Okay, so today we have Levin Guillermo, one of the PhD students in my lab, who is going to talk about his work. We've been together since I come to UF, so a few months, not even a year. And he's going to talk about the virtual manipulator, which is basically the idea of having manipulators, robotic arms attached to a spacecraft. And this is just to give you an idea of how Lagrange's equations are used in kind of real life, in applications and in research. So the purpose of this presentation is not really understanding the fine details, but just giving you an idea of how we use some of the theory that we study here for our work. And I guess, can we share these slides? I think we can share these slides with them later on. Okay, I'll give you this. Thank you so much. So you do your...
Yeah. Okay. Hi. So I'm going to talk to you about the virtual manipulator approach. It's a kinematic approach to, I guess, what it's for. Okay, so I'll just go over the outline of what I'll talk about. Is the motivation behind this approach, a little bit about dynamics of robotic arm manipulators in general, the virtual manipulator approach, what it is, its properties, its benefits, kinematic definitions, and how we form the equations of motion using this approach. And also I'll talk about one alternative approach to dynamic modeling of space robotic systems and some important points I wanted you to get from this presentation. So the motivation behind trying to develop, so what the virtual manipulator is it's it just helps us write kinematic quantities for free-floating systems. And so what this is for space robotics. And so oftentimes we depend on EVA, extravehicular activity, for assembling, fixing, and servicing spacecrafts. They're costly and hazardous for any astronaut that's involved. And so one alternative is to send some type of robot to do this kind of work. And we envision this to be something that either works in tandem with the astronaut or completely replaces the astronaut for EVA missions. And we will need some types of robots for assembly of future space stations and ground installations on other extraterrestrial bodies. And ultimately, we kind of want to expand our human presence in outer space. And so the idea of space robots has been around for a while, but in order to actually use a space robot, we're going to need to know, we would need to know the dynamic model, so we don't necessarily need the dynamic model to develop the controller, but we would need it for a good controller. And so that's why it's important to investigate dynamics and control of the autonomous space robotic spacecraft systems. And it would help us develop more fuel-efficient coordinated motion control of satellite base and robotic arms. This, again, represents a safer alternative to sending an astronaut for mission-related tasks, and it helps us further advance applications of robots in spaceflight mission operations. And so, just talking about dynamics of robotic arm manipulators in general, the base serves as our inertial reference frame for a fixed base manipulator. So this means the robotic arm, but in a space robot, the robotic arm is mounted onto a spacecraft base. So it's free of external forces and torques when not actuated. And so the laws that govern its motion are the conservation of linear and angular momentum. And so this means that there's a dynamic coupling between the robotic arm and the spacecraft base. And so that means the spacecraft base can no longer serve as the inertial reference frame. And so what this physically means is that if the robotic arm on the spacecraft were to move forward, the base would move backwards to conserve linear and then it would reorient itself, however, to conserve linear and angular momentum. And so, stressing the point that we can't write the equations of motion with respect to the base anymore, they become very difficult to write. And so what the virtual manipulator approach is. So it was an idea proposed by Vafa and Dubowski in 1991. These people are from MIT, and they've done a lot of work on this kind of stuff, and then kind of stopped for some reason. So what it does, it helps us model the kinematics and dynamics of a free-floating spacecraft robotic arm system. So what it is, actually the next slide. it's composed of idealized kinematic chains. So this is the real space manipulator, and this is the virtual manipulator. So I guess the point I want to stress is that the virtual manipulator is virtual. It is an abstract quantity. But what it does is it maps the motion of the real space manipulator. What the virtual manipulator does is it maps the motion of the virtual manipulator to the real space manipulator. And what we'll see is that the virtual manipulator is much easier to write the equations of motion is much easier for the virtual manipulator than the real system. And so I said that the virtual manipulator is composed of idealized kinematic chains with massless links, so they're rigid bodies. The base of the virtual manipulator is called the virtual ground, and that happens to be the center of mass of the real space manipulator. And so the reason we choose the virtual ground to be where it is because when the system is unactuated, from conservation of linear momentum, the center of mass of the system is an inertially fixed point if there is no initial linear momentum. Or it moves in, but it's fixed to an inertial reference frame. So by doing this, position and attitude dynamics become uncoupled. So an important point, I want to stress this again, is that the virtual manipulator just maps the motion to the real manipulator. And the person who came up with this has shown that it can be constructed for several types of structures: open and closed loop chains, and revolute or prismatic joints, typical of a normal robotic arm manipulator. And the virtual manipulator, we can construct it so that the endpoint coincides with any point on the real manipulator. And so for us, we would be interested in the motion of the end effector of the real manipulator, so that's where we would want to construct it to. And so I said previously that the motion of the virtual manipulator corresponds to the real manipulator, in that the virtual manipulator, its first link represents the attitude of the spacecraft base. And how we model that in the virtual manipulator is that it's connected to a spherical joint. The first link is connected to a spherical joint attached to the virtual ground. And the remaining link rotations of the virtual manipulator links directly correspond to the real manipulator. So in that, there's an assumption that these links are just revolute joints. I don't think I've seen it for prismatic joints yet, but that's fine. And another important property is that the virtual manipulator does not change if the mass characteristics of the real manipulator do not change either. So the benefits the benefits of the virtual manipulator approach is that it helps simplify the inverse kinematic problem associated with manipulators, trying to figure out how, basically it's the guidance trajectory for our end effector, calculating the workspace of the system, path planning, and design of our control systems. And what Papadopoulos and Dubowski have found, so the same professor but different person at MIT, they found that they can prepare the trajectory motion to avoid possible singular configurations. And so again, a singularity in robotics implies that a degree of freedom in motion is lost. And so this means that the control algorithm will fail computationally, and the workspace of the robotic arm will become limited. But they've been able to mitigate this problem. So the kinematics of the virtual manipulator. So what I have on the screen is, these are, I don't want to explain exactly how you got them, But the point is that we draw these vectors, these position vectors, and they're defined this way, and there's a proof for it, such that they pretty much, they're on the body of the link, but they also are, how would I say this? They're pretty much on the body of the link, but they're not at the same time. I don't know.
So if you start from the first one, from center of mass, where is that?
This is rho K, RCM. It depends on how you construct it.
Well, that's an example where
right. They're just going to some generic point. Yeah. Yeah, but the point is, depending on how it's constructed. In the picture, they just chose some arbitrary point on the robotic system. Just link K, link K point M on link K. And this is how you get those kinematic, pretty much the position of our points. Oh, yeah. Okay.
So as I said, we don't need to see the details of this, but the key point is if you have a multi-body system like this one, the base, spacecraft, and a bunch of links after that, and there is no external forces or torques or moments, there is conservation of linear momentum and angular momentum. And the first one tells you that the center of mass will stay at rest in an inertial reference frame or continue to move at constant velocity. So you can use that as your origin for an inertial reference frame. And then you construct these abstract vectors. So there is definitions behind these vectors that can go from that center of mass point to any point on your chain of rigid bodies that you have. And you can also go to the very last one, which is what it's called there, the end effector. And so the bottom line of this, you want to be able to control this entire system so that the end effector is doing some maneuver, is tracking some trajectory, it's grabbing another object in space, for example. But at the same time, you want to maintain some control on the base because that's your spacecraft. And so by defining all these virtual vectors, that's why it's called the virtual manipulator, you can write the equations of motion, as I'll show you, in a way that it's manageable, and you can use Lagrange's equations because you're going from an inertially fixed point. And you can design a control algorithm that allows you to go with the end effector where you want and have the base controlled so that it doesn't lose orientation or things like that. Because as you can imagine, that object in deep space, if you start moving all the links, if you start moving the end effector, you will have an effect on the rest of the body. So this is an alternative to, for example, the Keynes method is dealing with multi-body systems. This is another way to deal with multi-body systems. And again, I don't want anyone to really memorize or understand any of the steps. It's just the idea that if you have an inertially fixed point, you can construct these fake vectors that allow you to still represent the motion of the system, because each one of these vectors is telling you how each single link is moving, even though it's not an actual vector that covers the entire length of the rigid body. I don't know if that makes sense, but that's the high-level idea. So you can do multi-body dynamics with Lagrange's equations by doing this. Does it make sense?
Yeah, I was just getting confused about how to.
That's fine. I don't think we need to define all the vectors.
Yeah. Okay. Well, the vector quantities are there if you're curious. You can look in his thesis if you want to know where they come from. But okay, so again, these are the vector quantities, and this represents our velocity, I guess, of an arbitrary point, how we would transform back. All these quantities are important when we write our kinetic energy, which is 1/2 times the inertia times velocity dot velocity. I mean, I'm being informal, but you know the definition. And so
that's for a rigid body, right?
That's for a rigid body. Yeah. So for a system of bodies, it's the summation. So the important point here is that when we do Lagrange's equations, we need to choose generalized coordinates. They need to be linearly independent. And so what we choose is There's a little bit of technicality I'll go into later. But what we choose to represent the system is using the system center of mass, the spacecraft base angular velocity, and the joint angle rotations. So here I am assuming the joint angle rotations are only of a revolute joint, so they just are a planar rotation. And I'll explain why that's important in the next couple slides. We also need a Jacobian. Pretty much this maps the, because what we do is we give the control system generally a desired, where we want our end effector or spacecraft base up, but the things that we actually control are the, well, what we would actuate are the system center of mass and the attitude kinematics of the base and the rotation rates. So this is just maps one set of states to another set of states. So basically, if you go through all these summations and construct the matrix as such, you can construct your, and this matrix encompasses the entire definition of kinetic energy. It's the translational part and the rotational part. And so it's a scalar quantity, so when you multiply that all out, it's very long.
So what is Z0?
That's our independent, that's our state vector. Those are, well, it's quasi-Lagrangian because, and I'll go over why that's a technicality. Because we use Lagrange's equations for a certain portion of the equations of motion. So I think that's the next slide. Okay, so I'll go over that in soon. But you pretty much go through that, and you get your equations of motion, and they're pretty much in the form of an inertia term times the accelerations of the independent, the generalized coordinates, plus something we call the centripetal Coriolis. I guess the vector, the way it's written, but it's equivalent to our generalized forces, and our generalized forces are pretty much composed of our control and disturbances, and our control, that's what, so once you figure out, there's a Jacobian that maps, because again, we're only controlling, we control the rotation rates, the attitude rates of the base and the center of mass, and we have to map that into something that we desire, which is our end effector and the spacecraft base, the location of that, and that's what the Jacobian is. So, constructing the equations of motion. So, they use something called a quasi-Lagrangian approach, which means part of the equations of motion are derived using Lagrange's equations, and the other parts aren't. So the translational degrees of freedom of the system, we can use the Lagrangian approach. They're linearly independent, and they're proper generalized velocities, I guess is the proper way of saying it. Now, the rotational degrees of freedom, some of them aren't proper generalized velocities, some of them are. So because I assume that the link rotations are only revolute joints, it's just a planar rotation. So those can be used as independent as our generalized coordinates when we do Lagrange's equations. But for the spacecraft-based attitude, we can't assume that, we can't use those generalized coordinates because, did you go over kinematics for the, okay. So that's because when you integrate angular velocity, it is not the angles. It depends on how you represent it. You know, use Euler angles or quaternions or whatever. And so, oh, okay, yeah. But you can't use those. So what we do is for the equations of motion corresponding to the spacecraft-based attitude, we use angular momentum. And so, yeah, and again, the point is because the integral of angular velocity is not angular position, unlike the integral of linear velocity is position. And that is a key point in this approach. And that's why it's called quasi-Lagrangian, because it's a combination of both methods. Yeah. So where this research has gone is that it's no one has ever been able to form the equations of motion for the full roto-translational motion, so the full three-dimensional motion. Because the inertia term becomes extremely complicated, and it's very difficult to gain insight into what's happening. But the planar equations of motion, they reduce down. They're still complicated, but they've been solved. And so I guess where I'm trying to go is to write the full roto-translational motion. That's, I guess, part of what I'm doing. So.
Do you have some simulations?
No, I didn't. No. So I was going to go over. So the virtual manipulator is only one approach to modeling robotic systems. There's another one called the dynamically equivalent manipulator. It's proposed by these people, Ling, Xu, and Bergerman from, I think they're from Carnegie Mellon. It's similar to the virtual manipulator, as that they both arrive at some abstract fixed base manipulator that maps its motion to the real manipulator. But the claim is that the dynamically equivalent manipulator can be built for realistic experiments in the lab, because the virtual manipulator is just an abstract manipulator in simplifying dynamic modeling. And there is a paper that claims that it is possible to form a singularity-free expression for the dynamic model. It's important when we do control. So I, again, as Professor Bevilacqua stressed, there is, I don't really expect anyone to really get this. I'm still trying to understand it myself. But I guess the important points that I want to make are that in forming the equations of motion are very challenging. So how do we know that they're correct? And so what we can do is we can decompose the dynamics of the entire system by looking at certain portions of the system. And so the equations must reduce down to simpler motions when certain variables are constrained. And so what time does this class end? 12:35. Okay, so I have time. Okay. So what I can do is so to check, so what I mean by decompose the dynamics of the entire system and hold certain variables constrained is that we can look at what exactly is in these matrices, and we can look at, so we know that we know what the equations of motion are for a fixed-based robot arm manipulator. And so in the way we write our equations of motion, this encompasses our whole system. But we can look at a subpartition of the bigger matrix. And essentially, because this corresponds to the joint angles, the acceleration of the joints. And if we break up C plus into this, I guess this is what's called the centripetal Coriolis matrix. Yeah, so the ones at top are the equation of motion of the entire system. And so, yeah, I'm just trying to stress that we can always decompose the motion into little parts, and we can check those little portions. So the thing that that's in hashes would be our equations of motion for an equivalent fixed base manipulator. And so, and so we know that these equations of motion must satisfy a certain property. I guess the main one here is that this inertia tensor must be positive definite. And I don't know if he proved it to you, but you can take a class where that's all you do in attitude dynamics. But the other important property is that there is a relationship between this portion of the inertia tensor and this portion of the centripetal Coriolis matrix, and it's the skew symmetry property for a fixed-based robotic arm manipulator is an Euler, or you can write it it's an Euler-Lagrange system. And so I can, do you want me to prove it? I have it proved. Oh, okay, so you can go through that, and you have to see that the skew symmetry property says that that 1/2 m dot minus c, and you pre and post multiply by the vector, so you get 0, and it has to be 0. So, and then the last point I wanted to make is that we can look at how different terms arise from the Lagrangian approach. And so what this means, what I'm trying to say is that that I guess the easy one to see is that this has to be where our coefficients of our, I guess, part of our inertia tensor come from. Have to come from this one, because you're taking the time derivative of, well, there's here, kinetic energy is only composed of velocity, so there's no way you can get acceleration from it if you take its partial with respect to just the generalized coordinates. You'd have to take the derivative of it, and so that's another check you can do. And I think that's it. Okay.
Thanks. It's still working. All right, so bottom line of this is that if I can fix the microphone, we can continue. I don't know what kind of sound that made. So there was a comment at some point about Keynes dynamics and multibody dynamics. What this really is, and again, forget about the details there. There's a lot of definitions that Levin didn't go through about those vectors. The bottom line is that you have a multi-rigid body system. How do you deal with that? Because in this class we've seen particles, we've seen systems of particles and rigid bodies, but then when you start getting serious and you have things connected, which is what happens all the time in your engine's car, for example, that's the most immediate example, but this happens also in space where you may have, something with a bunch of links. This will be your spacecraft base here. So imagine that you have an inertial reference frame somewhere with its coordinate system. Well, and at the end you have some kind of hand-like tool that is supposed to grab something else, the end effector if you want, EE. Well, what you want to do is control this system. And controlling this system really means this guy is doing what you want, is going to follow some trajectory and reach some desired point in the inertial space. But you need to maintain some control on the base. You can't have these links moving and the base going crazy without control going somewhere else. Because if you start actuating all these links and you hope that this end effector goes where it's supposed to go, you will get, of course, there are internal reactions here that will make all the other links move. And so the spacecraft will go away, your system will go away, you will never drive this guy where it needs to go. If this was grounded somewhere, that would be easy. You put it here on the table, it's easy to move, not easy, but a multi-link manipulator, you can control it. But the problem is that in deep space, quote-unquote deep space, everything is going to move. You don't have anything attached to the ground. So that approach starts from the assumption that if this system is not actuated, the center of mass doesn't really go anywhere. Because if I look at this entire system from outside and there are no external forces or moments, especially forces, the center of mass will stay where it is in the inertial reference frame, or at the least, at most, it will move a constant velocity. So you can use these as an inertial eventually fixed point and define vectors from here. Those were all those weird vectors that you've seen before. And without understanding the details, writing the dynamics with respect to that point, it's easier, it's feasible. If you were trying to do it with respect to some other point, it will become almost intractable. And actually, it's easier if you do it in a planar case. It's possible if you do it in a planar case, which is where it was getting to with the final equation. But if you start adding the 3D component to this, it becomes extremely challenging. So we're not going to do any multi-body dynamics here. That's really not the point of the class. And the most of, the problems that we've seen and that we will see is at the most you have a rigid body of weird shape as we've done last time that has only one mass here and rotates inside the guide, or maybe this one that one of you has been trying to solve and will probably do it next time or sometime soon, where you do have two rigid bodies, one with the mass m and then another one with a smaller mass that it's moving inside of it. And so here you have gravity and things are moving at the same time. There is no friction here. So these two objects are actually going to move along the ground. And that's a multi-body system. Because there are two rigid bodies, and so you need, of course, at least two, that are exchanging forces here and actions here, and they're moving together. This is just a more complicated one. So when you get to more complicated problems, you can still use Newtonian approach and Lagrange's approach, but they may be, you may need tricks like this one, moving yourself to the center of mass so that you can write something you can actually manipulate and solve. And so after that point, yes, you can have Keynes' method, you can have a bunch of methods, but it really becomes a computational issue. You need to have symbolic toolboxes, good symbolic toolboxes to find your equations of motion. So I just thought I would give you an idea of what or how we're using Lagrange's equations in our group, and where is the limit in terms of doing things by hands. At some point, it's intractable, you cannot do it. So if we start, as we will see, we'll start solving even a problem like this, calculation can become pretty annoying. And so you may need a computer. I know there was a bunch of formulas that we don't need to understand, but that was really the point, that if you start doing multi-body dynamics, you need to find tricks that make your equations that even allow you to even set up the problem, not even getting to the equations, that you can start solving the problem. And I've tried myself at some point to do it symbolically, adding, even just starting to think that the spacecraft can only move in a plane, and the first link here, now it's has a little more freedom than just moving about this axis, that there is another axis of rotation that is allowed, and you try to do that in MATLAB in symbolic toolbox and it gets stuck. It will not give you a solution. It would just hang up there and give you nothing. So things can get ugly, and there are toolboxes. You need to, you use some computational tools to get somewhere. So I hope this just shows you that we're not teaching you junk, that this stuff is really used. It is used in publications. People are still trying to use it to find analytical solutions for complicated problems, or at least to have some sort of dynamics where you can close the loop. Many of you are taking the controls class. So without your equations of motion, you don't close the loop, right? There are control techniques that don't really need to know what kind of system you're controlling. But the best is obviously having the equations of motion so that you can close the loop and do things the right way, rather than brute force. You can still control something that you don't know well, but that's not the ideal situation. So since we have a little more time, I wanted to make a comment. So we need to finish this problem. We'll finish it next time, and we'll do a bunch of problems in the future before the test. We had this, right? And we said this is a weird rigid body that has all the mass at some point here. What did I call this? I called this M, point P. I don't know if this was O and this was C, whatever that was, Q. There was roll without sleep, right? And gravity here. This was the ground. And we already had found that there is a relationship between this angle theta and this other angle phi, right? By using the roll without slip condition. And we were trying to solve this the classical way with Euler's equations, right? With Euler's laws. So F equal m a bar in G, and a bar, that's basically the point P, because all the mass is concentrated there. We also said that H bar G happens to be 0, because it's just one point, even though it's mounted on a rigid body, which is empty in terms of mass. It's 1 point. And so what this tells me is that the moment of all forces with respect to the center of mass is 0. So that's actually one equation, or yeah, it's one equation, right? You already have that. We need to substitute what m bar is. We need to figure it out. But we know that it's 0. And then we were getting to the first part. I think we had found the velocity of P in G, right? And then from here, you take your ddt again, and you get a bar G. I don't think we've done it last time. And then the free body diagram is what we probably have not done. No, I'm not sure. Free body diagram. If I look at that rigid body, I see the following. I see the mass up here, mg. And then what do I have here? Did we do this? There is reaction from the guide, which is always pointing at the center. Call it n. But then there must be, we said this the first time we started doing kinematics with rolling as well. There must be some static friction that makes the disk roll, right? So call that F sub F. So we have these two forces here. And you need to take that into account. So your F is mg plus n plus F sub F. I'm not going to, we'll solve it next time, but I'm just trying to refresh where we were last time. And we had all the coordinate systems defined so that we can project all these forces appropriately. So that's, I told you, please continue solving this problem. So you have these forces here that will go into this first equation, the first law of Euler, number 1. And so that's your F, acceleration of center of mass, you figure it out. And so how many equations do you get from that one? So from 1, how many equations do I get? It is time that we start thinking about what we get from the laws that we have, how many equations we get, if they are enough, if they are giving me what I need, if I can eliminate things that are unknown, because that's really the point to getting equations of motion. You don't want to be stuck with unknown forces. I don't know those two. I don't necessarily care about those two, but if I'm using Euler's method, I mean Euler's laws for rigid body, I need to deal with them somehow. I should get 2 equations, right? Because, well, this is a planar problem. So I believe we had some inertially fixed reference coordinate system here, which I honestly don't remember how it was ordered. I have it in my notes somewhere, something like this. So it's a planar problem, so I should have 2 equations from F equal ma bar G. 2 equations, 2 unknowns. Can I really get my differential equation of motion? Remember, these only required 1. You think I can eliminate both of them? I don't think so, right? And so I will need a third one, and the third one will give me the additional equation. How many do I get? Well, I already told you, I get 1, because when I start doing, all the forces are in the plane of the board, all the position vectors are in the plane of the board. When you start doing your cross products, they will all be along the EZ direction, plus or minus, I don't know. But this will be only 1 equation. And if you do it with respect to the center of mass, which is this point here, the gravity will not contribute, but these 2 will be there. So that's your third equation. Now you have 3 equations, and you can play around and probably eliminate your unknowns. And I really don't care about the end result. I told you I don't care about the algebra. I just need to see that you know how many equations you need to write in order to get rid of the unknowns, right? So if you tell me that, for example, this is sufficient, that is not right. You can't get an equation of motion from that one. If you do moments with respect to center of mass equals 0, I don't even see the theta double dot appearing. How can you get a differential equation of motion from that one? Or if you stop at F equal mag bar, you still have these two there. Now, we'll finish it, but there was one thing that I wanted to tell you in order to solve with Lagrange's approach now. So if you were going to solve with Lagrange's equations, how would you do it? Most of the problem is already solved, right? I need let's just go to the bottom of this. This is just one variable, right? So this is really what you end up doing with Lagrange's equations. If you pick theta as the variable, you have one Lagrange equation, right? I know I want one differential equation of motion, so I know this has 1 degree of freedom. We proved what is the relationship between theta and phi, so you choose which one is your variable and go with that. So you will have to implement this. And for t, well, you're fine. T is what? 1 over 2 m v bar g dotted with v bar g plus 1 over 2 h bar g dotted with omega of the disk, which I think we called b. I'm not sure. I think we called it the b reference frame. So that would be your kinetic energy. And so this was done already. See, kinematics, you have to do it anyways. It doesn't matter how you're going to solve the problem. You have to do it. That's the first thing you do. This is there. We have it, whatever this v bar g is. What about this one? 0. This is a weird rigid body with one mass in one point, but still a rigid body. So the kinetic energy, you have it already. Now, the difficult part of Lagrange's equations are two, we said. It's kinematics, that's always the difficult part of any problem, the geometry of motion, and then figuring out this one. Now I'm asking you, what are you going to put in that? Because that's f, and I'm going to write the same f for now, the same symbol, and that will be dotted with the partial of the position of the center of mass, with respect to theta. Right? What are you going to put here? This? Why not? Okay, which ones you don't want? N. That's one. That's an obvious one. That's it? Remember when we defined the virtual displacements, I said, yeah, there's some constraint, and my particle, when we started from a particle, it's moving on this constraint, but this, when we define virtual displacements, I'm freezing these constraints. So this roller coaster here may be moving around in general, but I don't care, I freeze it. And so to keep me on track, I need this. And we said in general, it's a normal force that keeps me there. And you may have friction, but when you freeze it, you don't care about the friction, right? Because it's frozen. There is no actual motion. There is no elapsing of time. There is no relative velocity, so the dynamic friction is not there. What about the static friction? This is static friction. Is that a constraint force? It is a constraint force. Actually, I think we said last time that rolling without slip, it's a kinematic constraint, but there is a force that allows you to have that constraint, and that's the friction, the static friction force. In other words, if you freeze, say that this guy is able to move in time, but I'm still telling you that there is roll without slip, you still need that force to give you roll without slip. So it is a constraint force that allows you to say that the velocity of this point Q, doesn't matter if it's on the ground or on the disk, is the same. In this case, the ground is not going anywhere, so it's 0. but this could actually move around. You will still need a static friction force between the two so that you can have roll without slip. So that friction force actually is a constraint force, and it does not make any virtual work because this point has no velocity. When you freeze in time, you're constrained. Does it make sense? Can you relate back to that concept of freezing the constraint? This circular guide outside can move around. I don't care. When you define virtual work and virtual displacements, you freeze it. So here it is, frozen. When I freeze it, these two forces don't make any virtual work. So they don't need to go into the Lagrange equations. And so here you will only have mg. That is so much nicer, right? So this is one of those problems where probably doing Lagrange's equations is going to make your life much, much easier, because if you do it the classical way, the Newtonian way, it's perfectly fine, but you have two annoying unknowns, n and the force of friction that you don't know, because static friction you don't know. The dynamic one, yes, we have models for that, but not for the static one. And so if you do it with Newtonian, classical mechanics approach, you have to manipulate all these equations. You have to figure out how to eliminate them. There's no escape from that. Well, it happens that those two go away with Lagrange's equations because they're both constraint forces. It's pretty cool, I think. So I'm serious. You guys should really finish this with both techniques. I'll probably continue this, and then but it's good for you that you go to the bottom of these problems and you convince yourself that you are on the right track to get what you need, which is your differential equation or equations of motion. You need to be confident that you will have enough equations to eliminate unknowns and give me the differential equation of motion. So if you only watch me doing the problems, I think I told you, it's like watching TV. You don't learn much from watching TV. You have to do it yourself. So, and the other problem that I'm going to solve, so I'm really at the point of giving you homeworks. Even though I'm going to solve these things, or at least get them started for you, it's good that you try to do it yourself. It's the one that I told you before. This is one of your colleagues who said, this looks like a cool problem, and so we're doing it. There is this weird circular guide here that has a mass, so this is an actual rigid body, which is moving on without friction on a flat surface. There is gravity here. And inside this semicircular guide, there is a disk, which this time is not a weird disk, it's a uniformly distributed mass disk. So it's a regular one. And there is also roll without slip between the two. And as I told you before, this is a multi-body dynamics problem, because there are two rigid bodies. So it's more than one, it's multi-body. And so roll without slip, you need to find, I think, the same kind of setup is given to you. This is one of the problems in the book, by the way. I don't think there is a solution, though. Yeah, chapter 5 doesn't have many solutions, right? I think you're given that angle and some angle with another point on the disk, something very similar, theta and phi. And you need to find the equation. Oh, and also, and there is an x. Yeah, right. So you need to find the equations of motion of these in terms of x and theta. This is what the book is asking you, I believe. So this is already telling you that this is a 2 degree of freedom problem, so there must be a similar relationship to what we found last time between theta and phi that will come from the condition of roll without slip, except now the constraint is moving around. So this is exactly like that one, except the disk is uniform instead of weird with a mass point at some location. And I don't have the full track, and this has a mass, but it's very similar. Same here. The disk will see a reaction here, a friction force here that keeps the condition of roll without slip respected. So these are two constraint forces. If you do it with Lagrange's equations, they don't go there. So we'll try to do it both ways, or at least approach the problem both ways. because I think that's the best, to see the benefits of one approach or the other. Okay? So we don't have class Monday. We'll see you again on Wednesday. We'll do 2 lectures, one here, one in the room next door. And it will be a great idea if you try to finish these 2 problems by yourself, or at least get them set up so you're confident, okay, I have the start, I know where I'm going. And then we'll continue. Thanks.